All right, so this is a video about calculating confidence intervals. I had a student ask me for one, and I'm always producing videos, and I was just thinking, wow, I don't really have a video dedicated just to confidence intervals. So let's get to it. So just to get started, to understand a confidence interval, we have to understand the sampling distribution of the mean. So imagine that this is a population, could be a population on anything, could be something like a test score of somebody's body mass index, somebody's or height, just body mass index or height or anything, right? Some measure of speed or something like that, right? And this is the entire population. This population is centered at 0, so this is actually a standard normal distribution, but that's not, well, it is important here, but let's move forward and not just talk about that at the moment. So this is a normal curve, and so we're dealing with a normal distribution in this case. A normal distribution looks like a bell, right? All the values are surrounding the mean. In this case, the mean is centered at 0, and we know between plus or minus 2 standard deviations, so it's -2 and +2 standard deviations from the mean, we have 95% of all values. When we do statistics, when we conduct research, we're interested in collecting data from samples to make inferences about the population. It's not always possible to get every member of the population. However, we have access to samples. The samples are designed to capture a good representation of individuals in the population. We call the population of interest the sampling frame. So it could be, again, we're looking at body mass index in high school students age 18 years old. So that would be our sampling frame, all high school students, say in the United States, who are 18 years old. That would be our sampling frame. It would be really hard for us to collect all those data. So instead, what we do is we use samples. And when we collect samples, some of our samples are going to have values greater than the mean. Some of them are going to have values less than the mean. In fact, as we move away from the mean, you'll see that the curve gets closer and closer to the x-axis, although it never really touches the x-axis, goes on to positive infinity and negative infinity. So some of these samples will fall further away from the mean, making them less representative of the population. If we think of this population going left to right here, accumulating samples going from left to right, samples at the left end have a very small probability of occurring, as do samples at the right end. They have a very low probability of occurring, right? And in the middle, you have these samples that are more like the population. So if I was to ask, does a sample belong to this population? Or is it different from the population in some way? Chances are the further away it is, the more likely it is to be different. The mean of all these sample means, so if we take the mean of all these samples, the mean of all these samples means is the population mean. The standard deviation of all the sample means is known as the standard error of the mean. And it's just basically, this is the same calculation as we do for the standard deviation for a sample, except for now we have to divide by the square root of n, and you could actually work that out and see why it is. But we have to account for the fact that each of these samples has some sample size, and n in this case is the sample size. These may be all samples of size 20, so in this case n would be 20, right? So the standard error of the mean, so this is not called the standard deviation anymore, although it's a standard deviation of the sampling distribution of the mean. It's known as the standard error of the mean, and it's sigma. Sigma is the population standard deviation divided by the square root of the sample size. And this is, of course, when we have access to the standard deviation of the population. When we don't, we can use a t-distribution, and we can use the sample variance as an unbiased estimate of the population variance. I actually have videos on all that stuff if you're interested. So calculating the confidence interval. So what is the confidence interval? It's an interval in which we believe with some degree of certainty we'll find the true population mean value, right? So it's the confidence interval surrounds whatever our sample mean is. So like say sample 4, in a sense, we make pretend that this sample is its own little population. It has its own sampling distribution of the mean, and we're going to calculate the confidence interval there and see where we believe the true population value for, like, say, sample 4 is, or where it is, right? A confidence interval should be contrasted to a point estimate. If I was to calculate the the mean of sample 4 and estimate that, use that to estimate population mean, that would be a point estimate. An interval estimate gives me a little bit more leeway there, right? So the confidence interval is the sample mean. And if you're not familiar with this, I have to keep on adding things here because I just want to make sure you understand. We use these Latin letters like X to represent sample values, and we use Greek letters like we did sigma to represent population parameters. So this is a sample statistic. So it's a sample mean plus or minus m, where m stands for the margin of error. And we calculate the margin error. And again, we're dealing with a normal distribution here, and a standard normal distribution. Z1 minus alpha over 2, where alpha is our probability of a type 1 error. I'm not going to go into all that here because I'm assuming you know that you're working on confidence intervals times the standard error of the mean. So I need to calculate the standard error of the mean. And if you're doing problems, Z problems, you'll have the standard error of the mean already. And 1 minus alpha is the probability we're looking for, right? So we divide alpha by 2 because when we're dealing with a confidence interval, the confidence interval surrounds the mean, right? It surrounds the mean. So you're going to have value that's below the mean. Notice we have plus or minus, we're going to have value above the mean. So we have to split our alpha in half for that. By the way, the complement of alpha is confidence. So if we're, for instance, have an alpha of 0.05, its complement would be 1 minus 0.05 is 0.95. If I'm doing a 95% confidence interval, alpha would be 0.05 because 1 minus 0.95 is 0.05. Doing this calculation will allow you to find the area in a standard Z table, right? Because the Z tables generally cover the what's that word I'm looking for? The percentiles, right? The proportion of individuals that fall at or below some specific Z value. So what this calculation will give you is that cutoff point, right? And since, again, a confidence interval surrounds the mean, we have to divide it by 2. So we're looking at the cutoff point on both sides. So that's something that hopefully you'll understand by now, but if you don't, that's something you want to practice a little bit. Okay, so, all right, so here's an example where we use an alpha of 0.05. Most people, for some reason, love to deal with an alpha of 0.05, a 95% confidence interval. That's become a heuristic. It's not necessary. You can do 99% confidence or 90% confidence intervals, alpha of 0.01, alpha of 0.10, not just 0.05. It depends on the situation. That's for another video. That's not for here. So here we have this Z value as part of the margin of error, Z 1 minus alpha over 2. For alpha is 0.05, it's 1 minus 0.05 over 2, which equals 1 minus Z1 minus 0.025. And it then gives us the Z of 0.975. So we want to find in one of those critical value tables, you'd want to find what Z value is associated with an area of 0.975. And it turns out that the value 1.96. So if you look at this figure, the little black arrows arrowhead is at 1.96, just below 2. So this 0.975 would be everything to the left, not just up to minus 1.96, but all the way to negative infinity. So that's the area that's covered. Again, we're moving from left to right up to that point. And because it's symmetrical, again, the confidence interval surrounds the mean. We have a positive 1.96. We also need a negative 1.96, positive 1.96 and a negative 1.96. So basically this value is below 97.5% of all values. So that's a symmetry. An important point is that outside of this value is 2.5%, and below this value is 2.5%. Sometimes you do Z testing and you ask for the critical value for a two-tailed test, and it's 1.96, right? Plus or minus 1.96, right? Because you have this symmetry here. I put an absolute value signs here. I put absolute value signs here to indicate that it could be plus or minus. All right, let's do an example. Scenario: do Danielsville high school students weigh more on average than high school students statewide? We're using the Rodriguez weight index, the RWI, instead of weight. This is a really cool weight index. I guess you figured that's my last name, right? RWI accounts for height and lean body mass being muscle and bone density. RWI scores range from 0 to 100, with higher scores representing greater progression to obesity. The RWI has a mean of 68 and a standard deviation. Mean mu, because it's a population value, right? And a standard deviation sigma of 15 for students statewide. So that's our population, right? So that's why we use Greek letters. Imagine that we collected data from a sample of 100 adolescents and their mean RWI was 70. So let's calculate the 95% confidence interval. All right, let's do it. So step one, we calculate the margin of error, right? The margin of error, we have Z 1 minus alpha over 2. We just did that, and we found it to be 1.96. We have our standard error, sigma, and I gave you sigma was 15. I said there was 100 students, so square root of 100. I try to make this as easy as possible on both of us. So it's 1.96 times, well, 1.5, right? 15 divided by 10, we get 2.94. So that's our margin of error. Step two, I like doing steps. Everybody likes steps and stages, so I do that. Calculate the confidence interval. So our confidence interval is the mean plus or minus the margin of error. In this case, our sample mean, we're not talking about the population, right? We know everything about the population. We're interested in the sample, see where our sample stands in relation to this population. 70 plus or minus margin of error, 70 plus or minus 2.94. So you subtract 2.94 from 70, and you add 2.94 to 70. So our 95% confidence interval, 67.08 and 72.94. Voila. Explain your confidence interval. We are 95% confident that the true population mean is between 67.08 and 72.94. So we see our point estimate is one thing, it's 70, but we say, well, you know, we're really confident that it's somewhere between here and here. Again, it's just a point estimate, right? More accurately, you could say if I took 100, well, if I took let's just follow what I have here. If we take all possible samples of size 100 from the population and calculate the confidence interval for each of those samples, right? 95% of the confidence intervals would include the true population mean, but 5% wouldn't. By the way, an interesting question, you know, that's an interpretation. An interesting question would be, here's a little picture of our confidence interval. So here's our true population, right? And here's our sample. So our sample has a mean of 70, and the population mean is 68, right? So you can see our sample mean differs from the population mean by like 2 units here, right? We see that 95% of all samples would include the population mean. And in this case, we pretend that 70 is our population mean. One question that people might have is, well, are the RWI scores in Danielsville different from the score statewide? Well, these data indicate that they are not, because we find the true population mean value falling within this 95% confidence interval. So we're 95% confident that any value in there belongs to our population, essentially, right? For it to be different, we'd have to be far away from that population mean, and that population mean could not be found within this 95% confidence interval. That would tell us that, say, like the population mean was out here, it would have less than a 5% chance of occurring, right? If this is our new population, right? So you can actually judge meaningful differences using confidence intervals. If the confidence interval includes the population mean, your sample does not differ from the population mean. If it does not include it, you can be pretty confident that your sample is different from the population mean, or your sample is different from the population. That's all I have for you folks. Thank you for listening and have a great day.